Good morning everyone. In today's lecture, we will see the type of channels that are commonly encountered, that is channels that have a low pass characteristic. We will also look at equalizers that are required to compensate the response of this channel to reduce the intersymbol interference as much as possible. Our channel looks like this. We have the digital input and this goes through a transmitter which gives it the appropriate pulse and turns it into a continuous time signal. And this is the channel, and after the channel we should have an equalizer. There is sampling, and finally there is the decision. So we said last week that we can have the filter, we can have a discrete time filter here, continuous time filter here, continuous time filter here, or a discrete time filter there. Okay. So there are four possibilities. We put it either at the receiver or the transmitter, and we can do it in the continuous time or the discrete time domain. So let's start with the discrete time equalizer. We can then go on to continuous time equalizers. What we'll do is to see what characteristics we would like from the discrete time filter that we want to use as an equalizer. So it's many times you see in books that you just have to invert the channel and that's enough. But you also have to intuitively understand what goes on when you do equalization. That's the only way you will be able to design in a particular situation. So we'll use a discrete time filter, and now we won't say whether we use it on the transmit or the receive side. We'll take care of that afterwards. So what are the types of discrete time filters you know? There are two types, right? Depending on the length of the impulse response, you have FIR filters and IIR filters. Which is the one you want to use here? Is there anything that pushes you to one type or the other? How would you decide whether you want to choose an IIR filter or an FIR filter? Here I am talking about whether we should use FIR or IIR filters for this equalizer. Let's assume that it is here, okay, in the receiver. After sampling the data, we have to use an FIR or an IIR filter. How would we decide which one to use? So let's say I wanted to exactly cancel the channel. You need an IIR. Let's say I tell you that the channel itself has an impulse response like this. This is the response of the channel, okay. It has 4 non-zero elements and it is 0 afterwards. Okay, let's take this particular channel response. It has, this is the cursor, which is 1, and it has 3 intersymbol interfering responses that are non-zero, and then the rest of it is 0. What kind of filter would you need to equalize this? Exactly invert it, let's say. IR, why? Yeah, the reciprocal of this will turn out to be IIR. So this is H of 0, H of 1 Z inverse, H of 2 Z inverse square, H of 3 Z inverse cube. The inverse of this is some polynomial, 1 over some polynomial in Z inverse, and that will give you, when you expand in a series, infinite number of terms. For exact cancellation, which means this is the channel response. When I say channel response, here I am talking about the sampled response of the transmitter and the channel together. Okay. This times the equalizer response should be 1. So in that case, it will give you exact cancellation. HCH, if the channel response is FIR, HCQ must be IIR. Another way to think about it is, when you cascade 2 filters, you convolve the impulse responses. Okay. So let's say this is the impulse response of the channel. Okay. You have 4 non-zero elements in the response. And how do you compute the convolution? By flip and overlap and multiply. Okay. So let's say the impulse response also had some finite number of elements, some FIR filter. What happens? As you flip and you slide the last element to here, there is only one product, right? That will not be 0. So you can never get an FIR times FIR to be something which has a single 1 and all zeros. Is this clear? As you flip and slide, when only one of the equalizer's elements is overlapping with one of the channel's impulse responses, you will always have non-zero. Okay? You cannot make a single 1 and all zeros with a product of 2 FIRs. And that is what this is also saying in terms of power series, but this is a more, this is a time domain way of saying the same thing. So now what if the channel response is IIR? In fact, for the RC case that we took, what was the type of response, was it infinitely long or finitely long? Infinitely long. Okay. So what is it then? What should the equalizer be? Again, for exact cancellation, should be FIR. Why do you say that? So should it be FIR or IR? I think IR. Why? Exactly. So firstly, if the channel response happens to be representable by 1 in the numerator and some finite number of terms in the denominator, so n going from 0 to n, then this can be inverted with an nth order FIR filter. But if the numerator also has, even if this goes from 0 to 1, you will have an IR response when you invert it. If we do have an IR filter, we can exactly cancel the ISI. That's what this is saying. So what is then the difference in implementation between IR and FIR? Is there any reason to prefer an FIR? Okay, think of something else. What about implementing FIRs and IRs? What are the differences? FIR, you will need a higher order to match the response of some IR. So that is still something that is to be said for IR. It looks like you can do more with less using an IR filter. What else is an advantage of an FIR? So there is a problem with stability that is not just in this kind of impulse response level itself. When you talk about complicated digital filters, there is quantization of coefficients, and that's why it can move out of unit circle and so on. But for us, we are particularly looking at very high speed implementations. So you don't have feedback in an FIR realization, but you do have feedback in an IR realization. So for instance, you make a first order IR using a structure like this. So this by definition implies that a delay around this loop is equal to the sampling period Ts. So if you have excess delays in the loop, you can get instability. And you already know that by simulating the D flip-flop and so on, the output of a D flip-flop, for instance, in the ideal representation, when the clock changes, the output is supposed to change with the clock. But then what do you see in the simulation? There is a delay. And how much is the delay? In your case, like what was the value of the delay? How many picoseconds was it? 250 to 300 picoseconds. Okay. Now let's say you are talking about even 1 gigahertz, 1 gigabit per second signal, which is not a very high rate these days. It's 1/4 of the period. Okay. So you have, if you try to make such a delay, so flip-flop can be used as a delay element in some cases. We'll come to that later. If you do make such a delay, you have an extra delay of e to the minus st, where t is a significant fraction of ts. So typically you can't make IR filters very well, especially at very high speeds, because you cannot close the feedback loop. The feedback loop can have excess delay, and particularly with the emphasis on high speed implementations, you can't do this. If it's at low speed, that's okay. You can convert all of the analog signals into digital signals and make a digital FIR filter. And as long as digital circuits are working as they are supposed to, it will be fine. But that is not the regime that we are looking at. Although many of the equalization techniques can be used there, that's not where we are looking at. You are looking at some signal and then feeding it back into this. Or another way to think about it is this, the block that you wanted to implement was, I'll write it in the continuous time type of representation, something like this, right? And then you can have more taps. You will have more taps typically. What is the transfer function of this? E to the minus sts by 1 plus alpha e to the minus sts. Now if you have another e to the minus std here, what happens? Clearly the locations of the poles have changed. So there will be a problem of implementing IR filters at very high speeds. That is one issue. There is another issue at lower speeds. Maybe you can implement it, and this is something we can only see afterwards, after we see the details. But it turns out that adaptation is more difficult with IR filters. Adaptation refers to varying the coefficients so that it matches the channel exactly. So the channel may be known in some cases, but may not be exactly known in other cases. You need adaptation. Adaptation is a way of automatically choosing the coefficients so that to an unknown channel you get the correct equalization. Okay. So firstly the channel may be unknown. Not that it's never like completely unknown. It's not totally arbitrary, but there is a huge range. The simplest example to think is you are connecting two channels by a pair of wires, and the wires can be long or short. just like your Ethernet cable, right? You can have your computer and your router is sitting next to it, and that is a short cable, or you can you have the wiring through the building, which can be like 100 meters long. So it can be from a few meters to few hundred meters. So the equalization required for one doesn't work for the other one. Okay. That is a varying channel. And secondly, even if it's a fixed channel, things do vary with environment. If the temperature changes, things will vary. And the environmental changes affect both the channel and the equalizer itself. Okay. For instance, let's say you make an equalizer on a chip and the temperature changes. What happens? Could the response change? How? Why would the response of a filter that you make on a chip change with temperature? Component values will change. I mean, the simplest thing to think of is the transistor GM, right? Especially if you have a bipolar transistor, it is directly proportional to absolute temperature. So that will change. So if you have amplifiers that has a factor of GM in it, that could change. Okay. So both of these will change, and the equalizer has to automatically readjust the coefficient so that overall you have the nice, good equalized response. Okay. Now what happens is, when you have an IR filter and you try to adapt it, now you have to take care that over the entire adaptation range it is stable, and the adaptation process itself is a bit more complicated for IR filters. So because you have a many tap IR filter, you have to make sure that for every possible combination of the coefficients it has to be stable. Okay. If you are adapting it. For FIR there is no problem, meaning any value you set, it will still be stable. So adaptation is more difficult. For this reason, we typically tend to use FIR filters. Although IR filters seem to give you an advantage of having fewer taps and so on. Just having a fewer number of taps is not enough. It has to be implementable with lower power and with reliability. So for that we do use FIR filters. So let's see what we can do with FIR filters. So let's say my channel consists of just one post cursor element, okay, and everything else is 0. This is also just to get you a feel for what kind of impulse responses you need. Okay, so it's possible to do everything mathematically. If you do one general thing, everything is included in it, but it's also a good idea to know what happens in each case. You have a single post cursor ISI. This is the response of the channel. What is the type of what kind of equalizer would you want for this? How many taps would it need? Ideally, of course, you need an IR response, but let's say I tell you that you have to use FIR. How many taps will you use? So clearly the response I want in the ideal case would be this. So give me some number, like are you going to use 5 taps for this, 3 taps, 1 tap? So how many will you use? 100, 1000, 50, 10. This is the equalized channel that I want, and the equalizer response. He says it has 2 taps. I will weight one of those taps with, let's say, 1 arbitrarily. Okay, I can choose the rest of them to be anything I want. So would I put the equalizer tap before or after this? After. Why? Before or after? So this is G of 0. Okay, I want a 2 tap response. Would I have G of -1 to be non-zero or G of 1 to be non-zero? G of 1. Why? This 0 is basically whatever it corresponds to that 1.0 tap. Okay, I can have some things before it, I can have things after it. You want to put it here and you want to make it negative. Okay, so when you flip it, so this is H of 0, H of 1. When you flip this, it is here, and then when you slide it by 1, sorry, this is negative, and when you flip this and slide it by 1, it's here, and when you slide it by 2, it's here. So what is the response I can get? In this case, this is 1, right? So I simply get H of 0. The next case, what is the value of this tap? Yeah, minus H0 by H0. This is H1 by H0. Yeah, you are multiplying this by H0 and adding it to H1. And also it makes sense that it is H1 by H0, because if there is no ISI, if H1 is 0, they should go to 0 also. So the next one will be 0. And what is the next one going to be? H0. And it is assumed that H1 is less than H0, okay, because my cursor is where the peak occurs in the response, right? When I send a pulse through the channel, I get something, and I sample at the peak. Somehow the clock is adjusted so that it samples at the peak, that is H0, and everything else is clearly less than the peak, so that's H1. So is the equalized response better or worse than the original one? Here also we have 2 taps, right? Here we have the main cursor and this one. Here also we have the main cursor and it is 2 positions away. Is this better or worse? Better. Why is it better? H1 by H0 is less than 1. So we have H1 times something that's less than 1. So the amount of ISI is reduced. So this is better. And with 1 tap we were able to equalize it. What happens? Can we do better with 2 taps? Sorry, this is actually a 2 tap filter, right? There is one main tap and another tap. So if I have 3 elements in the equalizer, will the response be better? Can you make it better? It will become worse. Yeah, that's right. So I have this convolution. What are the resulting elements? I flip this and slide it and add it over. So I have, this is the cursor, right? What is the next one? And this I make equal to 0. And I have, and this also I want to make equal to 0. And what is the next one? And this obviously I can't make equal to 0. So what will be the values? So let's say g of 0 is 1. What is g of 1? What is g of 2? Minus plus what? H1 square by H0. It will be better. Why is that? Because the last product is what? So it will get better as you increase the number of taps, and it will quickly, you can make it go to 0 because each time you are multiplying it by some number less than 1. This is H0 square or H0? H0 square, right? Is this okay? How equalization works? So if you have more and more taps, you can reduce it. You can never reduce it to 0 with a finite number of taps, but we can make it small enough. Okay? Because you have, if this is the intersymbol interference, and that times H1 by H0 to the n minus 1 if you have an n tap filter. Okay? So this is the residual ISI. Now, depending on H1 by H0, which is basically how low pass the channel is, right? So if your pulse is like this, you sample here and here, H1 by H0 is a small number, but if your pulse is very broad, if the two are like this, then H1 by H0 is close to 1. So if it is close to 1, you need a large n to equalize it. Okay. So depending on the size of H1 by H0, you can still get better equalization by increasing the number of taps, but you don't need an infinite number of taps. So let's say H1 by H0 is 0.5, and if you have n equal to 4, what do you get? What is this number? Actually, let me not, I think I should have taken H0 also to be 1. So that would make things easier. If I take this to be 1, I'll get H1 to the n, that's all. So 0.5 to the 4, how much is it? 0.0625. So it's become some 6% of the main tap, and if you add one more tap, it becomes even smaller and so on. So the number of taps you use depends not only on the number of taps in the channel response, but also on the size of the intersymbol interference. So you can make it better, but you don't have to go to infinite number of taps based on how many you have in the, how many non-zero taps you have in the channel impulse response and the size of those taps. Any questions on this? Number of taps depends on and the magnitude of ISI. And what else can you say about the sign and magnitude of the taps of the equalizer? So G0, G1, G2. This is 1. G1 is H1 by H0. So if the ISI is large, then the equalizer tap also has to have a large magnitude. What about the sign? Negative. Why is that? Is that always true? It has to be, right? Because we have intersymbol interference with a low pass type of response. If both the cursor and the next one are positive in the channel response, the cursor and the next one in the equalizer should be of opposite signs. It is the negative of this. So it has the same size and the opposite sign. And also for this particular case, the tap in the equalizer was after the cursor. Is that always true? Is that how you want it always? Can you have taps before the cursor and do something useful? So that is, instead of the equalizer being like this, okay, now in this particular case we got something of this sort. Can we have taps before the cursor? Will it do anything useful? So can you think of any kind of channel for which you need a cursor before the, when you need a tap before the cursor in the equalizer? If the channel has precursor ISI, then the equalizer must also have a precursor tap. That is, instead of the, so we considered a channel response like this, but let's say the response is like this. Again, the 0 is basically at the location of the peak. It does not imply that there is something in negative time. So if you have this, then what is the kind of response you want from the equalizer? You want something of this sort, so that when you flip and add it, you will get the cursor and you can cancel the other one. So whether you have precursor taps in the equalizer depends on whether you have precursor taps in the ISI to start with. It depends on if the channel has precursor or post cursor What would you expect from any filter, any channel? Would it have post-cursor ISI, precursor ISI? There will be no post-cursor. No, causal does not mean there will be only post-cursor, okay? Because the response can be like this. So the peak is here, and let's say this is TS. So again, precursor does not mean the filter will respond before the input is applied, right? It only means that there is a response before the peak response of the filter. So there can be something here and there can be something there. But typically, most responses do look like this, right? They achieve a peak and then they take a long time to die out. Why is that? What is that type of response called? I mean, why do responses look like this and not like this? Think about it. It can have a precursor ISI. It can have a lot of precursor ISI also, but typically the number of post-cursor taps is much more than the number of precursor taps. Finally, we got a response like this. The second one was negative, the third one was positive, and so on. What do you get in the frequency domain if you have a response like this? This should be high pass, right? This is on the discrete time frequency axis. Okay, this is omega equal to pi. And you have an FIR response. So what does so you have 1, right? The DC gain is 1 plus alpha, and the high frequency gain is what? 1 minus alpha. And if alpha was negative, it would look this way, isn't it? And this is the kind of response you want. So the first tap is invariably negative. The taps after that you can't say. Note that we have also been taking a very simple case where we have ISI because of low pass filtering. That is the most common case. But then you can have ISI because of other reasons, and you can have a channel response that looks something like this. So maybe it does something, and then after that, after a while, it can do things like that. That you can't say whether it will be negative or positive very easily. So, but because the ISI is because of band limiting, the reason for intersymbol interference in our case is band limiting. Because of that, the pulse tends to broaden. So you'll almost always have the first precursor and the first postcursor to be the same sign as the cursor. That is positive. So that means that in the equalizer, the corresponding taps will be negative. This also has some implications on implementation. Okay, if you didn't know what the tap value would be, you would have to adjust it to take on like both positive and negative values. But that's not the case. At least for the first post and precursor, you can easily say that it will be positive. Okay, can it be negative? What does it mean if it is negative? This is the response of the channel. Can the first postcursor and precursors be negative? Is it possible, or is it some practically not seen, or what is it? What would it mean if the first postcursor, let's say the first postcursor ISI, that is negative? That means that the output is varying like this. Okay, in one TS it is going from positive to negative. In fact, this has a high frequency boost. It's just that in practice you don't see it. You can always make up responses like this. If you have a filter whose response is like this, you will get an ISI which is negative. But in practice, we are already so short of bandwidth that we don't see responses like this. If anything, we will see something of this sort. So what does fast alternation mean? That means high frequencies, right? So that means the output is output has a boosted high frequency. So this won't happen. And more likely, what is going to happen is it takes a long time to die out. So because it's a low pass channel, you can't have it. That's all. It's not because of any fundamental limitation. You could potentially have negative postcursor and precursor. And if you go far out from it, I'm not talking about the first one, but if you go far out, you can have both positive and negative. It's only the first one that you can reasonably say is positive. That's because you only get low pass channels. It's harder to transmit higher frequencies. First post and precursor taps of channel response positive. So this implies that the corresponding ones in the equalizer are negative. So that's it. You know how to make an equalizer. If you know the channel response now, you can make an equalizer, right? So if you have more taps, you will have more terms to deal with, and you will have more equations and more variables. Here we always had two terms adding up, so we could just by inspection write down these terms. If you have H0, H1, H2, H3 and so on, these will have 4 terms, let's say 4 non-zero terms. So you'll need 4 simultaneous equations to solve for G. Okay, so, but you can solve it nonetheless. There's nothing complicated about it. Now let's say I give you H. Are there other ways of choosing or is this the best? What was the basis of choosing the taps? I mean, choosing the equalizer taps. I know the channel response, okay? So now I want to design an equalizer for it. I first of all maybe arbitrarily decide the number of taps that I want. Okay, then I go and put those tap values. Let's say I know the channel response. I decided that I'm going to use a 4 tap FIR equalizer, and I want to determine the coefficients of these taps. What was the basis here? How did we determine the taps? So we cancelled out all the inter-symbol interfering terms as much as possible. I mean, the ones at the ends obviously we cannot cancel. Okay. So is that the best we can do, or is there some other thing that we can do? So what was my algorithm? Given h of n, it's assumed to have some finite number of taps. Let's say it has 3 taps. Choose g of n to be 5 taps. So this is somewhat arbitrary, but I'm willing to work within the limitations of this, right? Now you can say why 5 taps, I can make it better with 7 taps. That is true. But let's say I am assuming I will have 5 tap equalizer and I want to determine the coefficients. How did I go and do that? So I compute h of n convolved with g of n, and roughly speaking I tried to get this as close to 1000 as much as possible. But I know that it's theoretically not possible because the last one will be overlapping and at least one non-zero element you will get. Okay. So what does our impulse response look like in this case? So let me say this is 2 taps. This is better. If I have 2 taps, how many this h convolved with g, how many non-zero values will it have? It will have a total of 6 taps. Of that, how many can I make 0? 4 will be 0. Why only 4? First one, last one was 0. Other way to think about it is, here I have g of n. So I can make the ratio of like 4 of them to any one of them I can choose. But beyond that, I don't even have variables to choose. Okay. So result is I have something like this, and 4 of them are 0, and the next one is either positive or negative. I don't care. I'll just draw it like this. So is this the best that I can do? That's my question. Anyway, think about it. We can discuss it tomorrow, Monday. Any question? No, my aim is to get maximum signal to noise ratio. So ultimately, when I sample the signal, I get something, and over that I have some noise. I want this to, so let's say I add a fixed amount of noise. So then I don't have to worry about noise at all. I want this to be maximum. Yeah, okay, let's say the noise is fixed. Once the noise is fixed, we don't have to worry about it, right? We just say we maximize the signal amplitude and that will be the best. Okay, but that signal includes ISI and everything. So right now, the way we have got it is, we have 1, then 4 zeros and this one. So what is the alternative? The only alternative now is to let these become non-zero, right? That's the only thing that we can do. But is there some combination there that will make it even better than this? Okay, is the question clear? I can choose this to be 4 zeros and 1 non-zero, or I can choose all of them to be non-zero or some other combination, so that the net effect is somehow less than this one. Is that even possible? Think about it. Okay, that's the end of today's class. We will discuss other methods of choosing the coefficients in the next class.